Okay, welcome everyone. Today we have Sarah Moran from LPL, University of Arizona. Sarah is a postdoc of Mark Malley, very busy Mark Malley. And she has received a PhD from Johns Hopkins, and her advisor had a same first name. Just wanted to mention that. So her dissertation was in search of clear skies, linking planetary aerosols from laboratory to models, right? Mm-hmm. That sounds very interesting. And today we'll hear about the hazy world, year and 5, through laboratory experiments. So, Sarah, it's yours.
Okay, thank you so much for that introduction. So what I'm going to be talking about today is mostly my dissertation work, in fact, so you'll get to hear all about it. So the reason why I study exoplanets at all and planets of all kinds is just because I'm mostly interested in this question of how far can we push what makes a planet? What are the limits of how a planet forms and how it changes and evolves over time? And so from the perspective of exoplanets outside the solar system, it helps us understand how we fit in, how Earth fits in as a planet and how all of the planets within our own system it gives them context. Are they a weird set of planets? Are they very typical? We can't know unless we build up this statistical population of all of the planets that we're able to measure. And on the other side, by actually staying within the solar system and not abandoning it entirely, we can get a much clearer picture of specific worlds. So we can take deep dives into their physics and their chemistry because they're so much closer, they're easier to observe, and we can actually send spacecraft to them for a really close look. To set the stage a little bit more, I just really like showing this figure, which I have stolen pretty blatantly from Hannah Wakeford, just showing all of the beautiful different kinds of aerosols that exist within our own solar system. So moving from left to right, we have the sulfuric acid clouds of Venus, the very, very thin water and CO2 clouds of Mars, Jupiter's great storm systems, this beautiful hexagon on the pole of Saturn, Titan's hazy skies. We have Neptune. I skipped Uranus because I think Neptune is prettier. And then Pluto with its very thin haze layer just glowing like that. I just like to show that even within our own solar system, clouds and hazes are very diverse. They're all different colors. They form all different sorts of structures, but they allow us also to trace the processes that are happening in these atmospheres. If we then go back to outside the solar system again, even though we have this great diversity of worlds within our solar system, we don't actually have an example of the thing that is most common in our galaxy, which is illustrated here by this histogram with this double peak of what I like to call super Earths and mini Neptunes. I know not everyone agrees with that definition, but that's how I like to use it, where these worlds not quite up to 2 Earth radii are probably terrestrial and therefore super Earths, and then things slightly bigger, but not quite so big as our ice giants, are these mini Neptune-like worlds. And so we have this kind of very basic picture of their size, but what else do we know about them? And I always really like to make the point that although we think that the densities of some of these mini Neptunes should tell us that they should be fairly gaseous, we don't actually know in most cases for most of these worlds. If you look at this somewhat frightening diagram where we're looking at radius on the y-axis and mass on the x-axis, and on all of these colored lines are different lines of bulk density for what these planets could be, from completely iron down here in the red, all the way up to a familiar gas giant in our solar system of coal, hydrogen, helium. And so you can see in some cases, they plot pretty nicely, or if we just look at our own solar system, like Venus and Earth, sit pretty solidly on this magnesium silicate iron region. But for a lot of these planets, if we look at these error bars, you can imagine them sliding back and forth, and we really have no idea what their bulk densities should be. And if we were to understand that better, that also lets us understand how these planets have formed, how they've changed over time. And so I like this figure kind of showing this hint of the radius gap that we saw earlier and different reasons why that could be so. Is it photoevaporation, where they form gas rich and then eventually their star erodes that atmosphere over time? Do they form gas rich and then the energy from formation itself is pushing out those those outer layers of the atmosphere, or finally, do they actually form more like we would think a terrestrial planet forms? And we can start to fill out this population, but without measuring their atmospheres, we don't really know. And so the way to do that in most cases, certainly the way that I think about most, is through transmission spectroscopy. And so I'm sure most of you are quite familiar, but for those of you who are not, I think it bears going over again. As we watch the planet pass in front of the star and look through different wavelengths of light, we can trace out the presence of particular molecules in the atmosphere or the size of the atmosphere. And so if we translate that then to graphical form, it looks something like this, where in this particular made up cartoon atmosphere, we're seeing hydrogen and potassium and sodium, sorry, excuse me. And I also always like to point out that this is not just something we do on other worlds that we have no idea about, that we want to know more about. You can see this very clearly if we look at the Earth's own atmosphere by paging through different wavelengths of light. And this is looking at the ozone band. You see that the Earth appears to pop out and get bigger when we're in the middle of that band, and then shrinks back down when we're outside of it. I also really love this image because you can see the moon in the background and how it's not changing at all in size as we go through these different wavelengths of light. So it does not have any ozone in its atmosphere, and in fact does not have an atmosphere at all. So I think that kind of illustrates what we're doing in a more tangible way. But it's not, of course, just gases that absorb and change our information that we get from these observations. If there's other scatterers or absorbers in the atmosphere, that changes the picture. And so this cartoon from Julie Moses is kind of illustrating two things that could be happening in a very simple case. On the bottom, if you're looking at a much more compact atmosphere, so maybe not super rich in hydrogen and helium, the atmosphere shrinks back down because those gases are heavier and held more tightly to the planet by gravity. And so a photon coming from the star just comes and pings us as observers, and we don't see anything. But on the other hand, if you have this big puffy atmosphere, like in the top, you have all of these gases that should be interacting with photons, but if you have this cloud layer at the top, that's maybe going to absorb, and again, we'll see nothing. So in certain low resolution cases at limited wavelengths, these will look exactly the same to us. And we're sort of just now at the point where we're able to measure mini Neptunes, not super Earths, that's still a little bit beyond what we can tell the difference, but these two cases from the last couple of years are showing us that we actually can measure the atmospheres of these smaller worlds. So this is K218b, which is a mini Neptune that we know has this really nice water feature here, probably also has some clouds that's maybe shrinking it a little bit. If we look over to GJ3470b, again, we're seeing this kind of trace of a water feature that's pretty compellingly showing us these do have atmospheres. They're mostly hydrogen with some water and also some trace cloud species. But this is very much at the limit of what we're able to do at the moment. In some cases, however, even when you do know you're looking at a mini Neptune, so this is GJ1214b, and its density is such that it has to have a substantial portion of hydrogen and helium in its atmosphere, we're still not seeing anything. So this top figure, these black points are observations from Hubble, led by Laura Kreigberg. And you can pretty clearly see that against these models, either a solar atmosphere, completely hydrogen, helium, and solar amounts of metals, or even a pure water atmosphere, the data pretty clearly rule that out. There's just not big enough features to see anything. And so you can imagine, okay, well, maybe it's not hydrogen and helium. Let's look at other possibilities. And so if you go down here, and now the green line here is a methane atmosphere and water, or even maybe a CO2 atmosphere, the data still kind of don't match that. It's even flatter than that. And so because we know from a density argument, it has to have some sort of puffy atmosphere, and we're seeing nothing, that's pretty compelling information that there is something else blocking our view of the gases. And that's likely some sort of cloud or haze material. Size of the particles that make up these clouds and or hazes also matters. It changes how we observe the atmosphere. So very small particles because it's a wavelength dependent response when the particles are small, tend to increase this slope here in Rayleigh scattering. And if you get bigger particles, you're in the me regime. And so you kind of just start to shrink these features and see this across all wavelengths. We also think that if we can get a handle on whether something is a cloud or a haze, which I promise I will define in just a minute, we're actually tracing evolution in temperature of these objects. And so at the hottest objects, we think we're making clouds of things like aluminum oxides, and then we move down in temperature to things like silicates. Eventually we get to salt clouds, but perhaps there's this suggestion that at some point below 1000 Kelvin, we're reaching this regime where hazes take over and are really going to dominate the observations of the worlds that we see. So as promised, when I talk about hazes, and there are people who would argue with me about particle sizes and other things, but when I talk about hazes, I mean particles that are in the atmosphere that got there through a photochemical process. So in this little cartoon, we're looking at Triton. And so it has its atmosphere, and then UV photons from the sun come and break apart the gas molecules that make up the atmospheric gases. They go through a whole series of different chemical reactions to build up these solid, very complex particles that are suspended in the atmosphere. And those are what I call hazes. Primarily, certainly in the solar system, this is driven by UV photons from the sun. But energetic particles from a neighboring magnetosphere, for example, or cosmic rays could also potentially drive this kind of process. But certainly in the solar system and expectedly in exoplanets, the host star is going to mostly drive this process. And the title here says we see clouds and haze across the solar system, but what I'm really hinting to is haze in this slide. These are sort of coffee stain images of Triton and Pluto, just to make the point that Triton, with its, although terrestrial, very thick atmosphere, 1.5 times that of Earth, has this very prominent haze layer. But then if we look to Pluto, which is microbar at the surface in pressure, we still have this very prominent haze layer that totally defines how we view the planet. Beyond just affecting observations, maybe getting in the way of our observations sometimes, haze can be really powerful because, again, it's a probe, it's a tracer of the processes that are shaping the atmosphere. So it can alter the bulk atmospheric composition as various gases get fed into as like sort of feedstock for making hazes, and maybe ultimately deplete those things that are we would otherwise see. It can also change the temperature structure of the atmosphere. There is work that's been done to show that Pluto, in fact, is being cooled and heated at various parts in the atmosphere based on the presence of its haze particles. And we know that Triton has an anti-greenhouse effect happening because of its haze layer. And finally, there's evidence to suggest that this photochemical process is starting to drive some really interesting chemistry that could be important from a prebiotic perspective, and making some really interesting building blocks if we care about life elsewhere. So that's setting the stage, sort of all of the background information I want you to have. And now I'm going to move into what we've actually been doing in the lab and what I did in the lab during my PhD to try to start to get at some of these questions we have. So most of the experimental work that has been done in the past and even now comes from what we know of the solar system. And so I'm showing here a little schematic of all of the different kinds of experiments that exist. So there have been Pluto experiments, Triton experiments, early Earth. This is my placeholder for super Earths, mini Neptunes, and then more hot Jupiter-like things. So all of this has been done, and this covers things, all of these different gases I've called out here on the more terrestrial side, things that maybe we think should be important in a more mini Neptune or super Earth-like context. But again, the vast majority of experiments have been done for Triton or the early Earth, and they've been done at room temperature. There have been experiments done as low as 90 Kelvin and as hot as 1500 Kelvin, but that's maybe 1 or 2 apiece at these extremes. And, dozens and dozens of them have been done at this room temperature place. And so we're just kind of really scratching the surface of what's possible. And we have learned a lot about clouds and hazes from solar system experiments. And so this is Triton here. And so we think that to drive this haze formation process, we need a reducing atmosphere. We know that oxygen-bearing molecules can feed into this thing that I talked about before with making prebiotic molecules like amino acids and nucleotide bases. We know from both experiments and spacecraft measurements, like from Cassini, that hazes are really complicated chemical beasts, and that clouds and hazes can interact. So for example, on Triton, there's a lot of evidence to suggest that the haze particles are actually acting as cloud condensation nuclei for the methane and ethane clouds lower in the atmosphere. But experiments have also kind of shown us that this whole sense of a reducing atmosphere is maybe not necessary, that if you start to oxidize the atmosphere, you're still able to make haze. And I'm going to talk about that a little bit more later on. But to move to what we actually have done at Johns Hopkins, we always start with Triton as our sort of base because so much work has been done to understand it both experimentally and then of course from observations. This is the setup of PHAZER. I really enjoy showing this picture because it's so clearly mad science. This is a custom built setup where, if I could find my mouse here, there it is. Where we flow various gas mixtures in through and control the pressure until it gets to this chamber here, which is where the experiment actually happens. And so we run experiments at about a millibar. And to the top here, we can attach either a UV lamp to mimic that, UV photon bombardment from a star, or we just attach a plasma source to just kind of kickstart some energy into the system to start breaking apart those gas molecules and seeing what we make and seeing if we can make haze. And so for these exoplanet experiments, we've done everything from 300 Kelvin, which I will call the habitable zone, or basically just that's easy because it's what temperature the room always is, up to something quite a bit warmer, like 800 Kelvin, which is about the limit of what we can do in the lab without having things melt on us. So we're really pushing the extremes of what's possible in our laboratory setting. And then we've done a whole bunch of different compositions, something from a CO2 dominated sort of terrestrial or maybe super terrestrial world. We've done these water dominated atmospheres in case that could be something that's actually common out there. And then to hydrogen dominated atmospheres like mini Neptunes. And then purely for COVID pandemic reasons, I also did a Triton experiment, which I will talk about at the end, but I promise I will tie it back to exoplanet observations as well and kind of explain how that's, again, feeding this back and forth between solar system science and exoplanet science. If you are really curious, these are the breakdowns of the different atmospheres we have run in the lab. And so, like I said before, we have these hydrogen dominated, these water dominated, and these carbon dioxide dominated atmospheres. And then we've, again, done the same thing at 800 Kelvin as a part of a new series of experiments. And this is what we make. So this is a snapshot from the first series of exoplanet experiments. And these are just images of the hazes on disks after we've made them and pulled them out of the chamber. So you can see that this is our Triton case down here, and that some of them look pretty Tritony. They're the same color anyway. Some of them don't make very much haze, but so it's kind of hard to get a sense of the color, but they all do make hazes, even on these disks that appear blank. We've measured under a microscope, and there are hazes on there. And then we also have this really interesting case with these hydrogen-dominated hazes at 600 and 400 Kelvin that they're green and brown. Which is really fascinating. And we have yet to fully understand why there are those colors, although we're working on it. And so, as I mentioned with the solar system, we're also seeing from these experiments that although there's this kind of powerful understanding, certainly in the literature, that you need methane to drive haze formation, that it's the primary precursor, which may be true, it could be the primary precursor to haze formation. It's not the only one. So in these cases, these water-rich cases, they made the most haze of any of them, and they have a lot of methane in the system. So methane is still really easily, powerfully driving this process. But down on this end here, this carbon dioxide rich case, it had carbon dioxide and carbon monoxide in the mix. There's no methane in here. The only carbon sources are carbon dioxide and carbon monoxide. And yet it's making actually the third most amount of particles of anything in this whole series of experiments. This has also been seen in a more hot Jupiter-like sense. So these are experiments done at JPL, where they also just started with a pure hydrogen and carbon monoxide mix, and they still ended up making particles at very high temperatures. Again, showing we don't necessarily need methane. Perhaps another carbon source is enough to start to drive particle formation. The particles that we make in the lab do vary in size. And so this is just breaking it down by the different temperatures, how the particle size changes, how the composition changes. So again, this is the hydrogen, the water, and the carbon dioxide mixes, and then whether or not it was a plasma or a UV lamp source. And so you can see they vary, and there are pretty clear trends here, but they do all stick kind of between 20 nanometers to maybe 200 nanometers at the max. So these are small particles, and for anything we care about, like with HST or UV measurements, this is mostly going to live in the Rayleigh regime and just drive scattering toward the blue rather than uniformly muting features in transmission spectra, at least if the hazes stay the size that they make them, which they might not. Shinting Yu is a postdoc at Santa Cruz, and she has shown through surface energy measurements. So her cartoon here is showing she has the disk with the hazes on it, and then she puts a water droplet on each slide and then measures the contact angle between them. And so that's showing kind of how sticky the hazes are compared to water and how much they want to bond, either with each other or with the water. And she's shown that in a lot of cases, these hazes are really sticky. They want to coagulate and grow. And so maybe, although they start from formation as being Rayleigh scatters, they can get bigger and maybe change what's going on as they start to interact with each other. So what I was interested sort of firstly during my PhD was the composition of these particles. And so that entailed me first dissolving them so I could do further measurements. And it turns out that that was actually much more challenging than I originally assumed, which is why I ended up with this horrible red, green, yellow plot. And so to break it down a little bit for you, this regime is the hydrogen dominated cases. These are the water dominated cases and the CO2 dominated cases. And the green, yellow, red shows how soluble they were in these varying, increasingly nasty organic solvents that I tried. So I always attempted first with methanol. And then if that didn't work, I just kind of kept going up. And so you can see in some cases, they never really wanted to dissolve. But if they did, it was always in a polar solvent. And so that's interesting. It's telling you something about the hazes themselves, because like dissolves like, suggesting that the hazes are primarily made of polar materials themselves. And we actually see that when we look at them under a microscope. It's particularly clear in this case here, they're starting to form these sort of linear chains of particles, which would make sense if they're polar, because they're trying to align themselves. Sort of more than just Sarah would like to do her experiments now, please. Knowing about their solubility can tell you something about how they're going to interact with other things in the atmosphere, like potential cloud species. So soluble materials, generally speaking, are much more effective as cloud condensation nuclei, or cloud seed particles. So this happens here. In this cartoon, we're seeing the brown dots are cloud seeds, which could be on Earth, for example, smog particles or sea spray or any sort of just solid that provides a surface for this water vapor to condense onto. So it lowers the energy barrier needed to transition from vapor to a solid or a liquid cloud droplet. And so this is critical on Earth. We very rarely actually in Earth's atmosphere reach enough supersaturation to just spontaneously go homogeneously from water vapor to water cloud particles. We almost always have this situation where there's a condensation seed driving that process. And that's not important only on Earth. This is probably one of my favorite papers that came out during my PhD, just because I think it's such a beautiful illustration of this process, that we see these high altitude clouds and the mid latitudes on Mars, water clouds, but models could not for the life of them explain how they got there. They couldn't make them, but we see them, we know they're there. And so Victoria Hartwick, who's now at NASA Ames, led this paper showing that if you account for meteorites impinging on the upper atmosphere and kind of vaporizing and becoming these smoke particles floating in the upper atmosphere, if you put that into the model, suddenly you make clouds exactly where you expect them to be, exactly where you see them. So this meteorite smoke is acting as an efficient cloud seed to have that water condense. So we know this is important elsewhere, not just on Earth, and I think it should be really important for exoplanets too. So now if we know things about how sticky the particles are, how soluble they are in various potential cloud species, we can start to understand them even better as cloud condensation nuclei. And so in the same paper that Shinting led, she showed that we have like these two kind of regimes of hazes of the ones that we made. We have some that have very low surface energies, so they're not going to be particularly cohesive. They're going to stay as these smaller particles and just kind of continue to build up in the atmosphere. They're also not very good as cloud seeds, and so they're not going to rain out of the atmosphere easily. And so we end up with potentially these very hazy worlds with these low surface energy hazes. And then others that actually have high surface energy are going to easily stick together, which means they're going to grow bigger, which means gravity is going to more efficiently pull them out of the atmosphere. And also they're going to more efficiently drive cloud formation, which then can rain them out through wet removal. And so that might actually, although we're making these hazes easily in this high surface energy case, we're also maybe efficiently removing them as well. If we go back again now to looking at the composition of these particles, which is really what I focused on, I'm showing you again a breakdown here of the gas phase composition of the starting mixture. So on the top here is our standard Titan case, and then these bottom two are the water-rich cases at 400 and 300 Kelvin. So you can see the composition of the mixtures is pretty different. They both have a lot of methane and some nitrogen, but then all of this water exists, of course, in the water-dominated cases. But then we end up with haze particles that look extremely similar. They're pretty much the same color. They actually made roughly the same amount of haze. So you might think initially that although they start from these very different compositions, they end up the same. But when we do elemental analysis on them, we see that that's not true. Although they're mostly carbon, which is expected, there's a lot more oxygen in the water-rich starting mixtures, which makes sense. There's a lot more oxygen to donate, to put into the solids, but that wasn't necessarily expected, that it would be so readily incorporated into the solid, but we're showing that it is. So to go a little bit deeper into what these particles' composition is like, we did mass spectrometry on them. This is a very simple schematic in case you're unfamiliar. On the y-axis, we have just intensity, and on the x-axis, we're looking at the mass to charge ratio. And this cartoon is actually from Cassini when it flew through the plumes of Enceladus. And so down at the lower end, you see things like methane and water vapor. And as you start to go to higher mass to charge ratios, you're seeing more complex species and complex organics.
What's the unit of the mass?
They're Daltons, so it's like 1 mass unit of an element. So like water is 1 hydrogen, or 2 hydrogen, 1 oxygen, so it's 18.
Okay.
Yeah. And so I actually want you to notice here that in this mass to charge space, this graph stops at 50. And we're going to briefly slide and zoom in here of my measurements from an Orbitrap mass spectrometer, which is very high resolution. And this one I've just chosen to illustrate here actually is at 250. So we're already at very, very complex species. And because this mass spec is so high resolution, which is in contrast to what Cassini flew, which is just unit mass, so just one mass to charge is all that it could resolve. Whereas here we're actually going down into these tiny individual peaks at like 10 to the 5 resolution. And so let's have a much better understanding where you're at these very high complex masses, there's a lot of degeneracy for what particular molecules could be. And so this helps us break that because we're at such high resolution. So again, we're starting at 50 here. Those Cassini measurements I showed you ended at 50, but these start at 50 and then go out. Actually, we detect species out to to about 800 mass to charge, but it gets messy after there. And so I'm stopping it here. So these are the hydrogen-rich cases, and to an untrained eye, it's hard to tell these apart, but these two are pretty messy, and that's because they weren't soluble, and so I was not getting any real clear signal from these measurements. But if you look down to this 300 case of the hydrogen-rich, it starts to have this very distinct kind of staircase structure, which is showing us repeating chemical units within the mass spec, which is telling us that, first of all, this material was soluble in the solvent that I put it in, and that we're getting meaningful results out of it. And what's different about this one as compared to the top two is it's the only one that the initial gas mixture had a nitrogen species in it in the form of ammonia. And so that seems to have changed the chemistry enough to make it soluble to mean that I could get results out of it. If we then look at the water-rich cases, this stair-step structure is much more apparent. And so again, you see this repeating chemical unit sort of behavior. Even then, it's different between the cases. So the 400 and 600 look fairly similar, but the shape of this is quite different actually between the 400, 300 case. And so that's showing that their chemistry is also quite different, even though again, they looked pretty similar, and also their elemental composition is fairly similar. How that those different elements are being incorporated is clearly different between them. If we go back to sort of more of a bulk composition picture, this is how it breaks down now with all of the species, not just those that had enough to do elemental analysis on. So again, this is carbon in the yellow, nitrogen in the green, the sort of turquoisey color is oxygen, and then the purple is hydrogen. And so you can see different amounts are incorporated into all of these different cases. It's kind of, there's nothing in particular looking at it this way that's, I think, compelling. But when you start to break it down within a particular composition, so these are just the water-rich cases, you see quite a bit different amounts of oxygen in each case. And what I think is really interesting here is this 600 Kelvin case had the least amount of oxygen in the initial gas mixture, and yet it has the most oxygen in the haze solid. Why would that be? That doesn't exactly make sense from our sort of simplistic what goes in, what comes out perspective. But this case of the water-rich case is the only one that had carbon monoxide in the gas mixture. And so it seems to have been a much more efficient oxygen donor into the solid particle as compared to these other two cases. And then in addition, I mentioned this earlier, that this 300 Kelvin case of the hydrogen-rich mixtures was the only one that was soluble enough for us to get meaningful measurements out. And I, again, think that is due to the presence of ammonia being in the initial gas mixture, altering the chemistry enough. And so these tiny changes in the presence or absence of particular trace species does have an effect on the solid composition. This is true in a couple of other experiments we've done. We did a high temperature case of a carbon dioxide mixture that also had hydrogen sulfide in the mix. And so this is showing the species with hydrogen sulfide in the mix and then without. And so you can see the separation between oxygen species changes between them. Obviously, sulfur products exist in the one with sulfur and not without. And so that's driving a difference here, this tiny bit of hydrogen sulfide. We see that, so these are, I should say, from the gas phase products. We see that also in the solid phase products, that we're incorporating this sulfur from this tiny bit in the trace, this tiny trace amount in the gas species, in the gas phase, sorry, into the solid as well. If we now kind of go back into the more complicated space, we can actually trace how these certain molecules are getting incorporated into the backbone of the chemical structure. So these are called Van Crevlin diagrams. They're essentially just elemental ratios. On the y-axis is the hydrogen to carbon content, and then the x-axis is the oxygen to carbon content, and then the different colors here are breaking it up by the temperature of the experiment. And so this is the hydrogen-rich, the water-rich, and the carbon dioxide-rich cases. And then these little shapes that I've outlined here are showing you where particular functional groups tend to plot in this phase space. So this middle region here are sort of amino acid-like things. Up over here are sort of fatty acids, carboxylic acids. We have sort of simpler hydrocarbons down here. And then as we move further out into higher oxygen to carbon ratios, we're reaching sort of carbohydrate or simple sugar land. And so the most interesting one is where we had all of those haze samples being soluble, and so we can compare them. And so you can see this 600 case that had the most oxygen has also the most oxygen in this phase space as well, where we're seeing more amino-like groups and more things that start to look like carbohydrates. We actually detected the formulas for several simple sugar species in this particular mixture. You can't quite see it because they're buried here, but we saw it in the 300 and 400 Kelvin case as well. That we're actually seeing not only amino acid-like things and nucleobase-like things, we're also seeing sugar-like things made from these experiments. And so that's starting to suggest that these materials could be really important for this atmospheric chemistry actually seeding the planet for the building blocks of life. And so there's the idea of where did life start, that it was maybe delivered extraterrestrially, or it started in the deep ocean. And so what this suggests to me is that the atmosphere itself internally can also be a critical part of that story. And that's very suggestive, but I don't want to run away with ourselves here. I kept saying sugar-like and amino acid-like is because although we've detected the molecules that are the molecular formulas that are consistent with those species, we can't actually measure the structure of the molecules that we've made from this mass spec measurement that we did. We'd have to do additional other sorts of measurements. And so it's compelling, it's intriguing, but it's not like a smoking gun of we have found sugar, we have made sugar in these experiments. It's like, this is a sugar-like thing, we should do more follow-up. So now that we have this solid phase chemistry where I'm calling out these potential molecules that we've made, and then we can compare it to the gas phase chemistry and whether or not there are these prebiotic precursors or organics being built. If we have an understanding of the initial gas phase chemistry that we put in, the gas phase chemistry coming out, and the solid phase chemistry coming out, we can start to try to understand the full chemical pathway to haze formation, which is extremely hard because there are so many different reactions that are happening. It's very difficult to reproduce in photochemical models, for example. They typically stop at maybe 3 or 4 carbons, whereas we're seeing things that have 10 carbons here. So this link between them from a modeling perspective is very much not done, but we're starting to approach maybe making progress on that front here. So that's sort of the end of the story from the exoplanet side, but not really. We're going to go back to the solar system for a moment and then wrap back to exoplanets. So Triton, which is here, you can kind of see in this little shadow of Neptune here, is a really interesting world to compare to both Titan and Pluto. They have very similar atmospheric compositions of mostly nitrogen with little bits of methane and carbon monoxide. They're all sort of roughly kind of the same temperature, floating about 100 Kelvin, give or take, 50 Kelvin. And they're in kind of different energetic regimes, where Titan is, of course, being hit by UV photons from the sun, but is also subject to Saturn's magnetosphere. Triton is in a similar situation, but it's much closer, much more deeply entwined with Neptune's magnetosphere, and then Pluto kind of lives by itself. It doesn't have a neighboring magnetosphere to drive any sort of additional chemical reactions. It's just relying on UV photons. And of course, there are different distances from the sun too, so they're receiving different amounts of that UV energy in the first place. So if we could understand the differences between these three worlds, maybe that would help us understand also much more different worlds that don't share these kind of similarities. And so we're again seeing this result that we saw from the exoplanet experiments, where methane maybe is not the end all be all to driving haze formation. On the top here, I'm showing PHAZER, Johns Hopkins work. These two orange bars here are kind of two end member cases of a Titan-like atmosphere where we kind of varied the amount of carbon monoxide in the mix. And you can see within error, they're making about the same. This is from my Triton experiment, where we're dialing down the methane a lot. So only 0.2% methane and 0.5% carbon monoxide. And we see way, way less haze. We still make haze, but at much reduced levels. That's not maybe particularly groundbreaking if we just look at this in isolation. But then if we turn to the PEMPRA experiments, which are done by a French group, they did a series of Pluto experiments where they tried to target Pluto at different altitudes. And so then they varied the methane and carbon monoxide abundance as a function of altitude for their experiment. You can see they also made varying amounts of haze. This is the production rate on the x-axis. I don't know if I mentioned that. And so you can see that as they go from this case to this case, where they dial down from 5% to 1% methane, they're drastically reducing the amount of haze that gets made. But what I think is really exciting here is they did this case with the same amount of methane, but they turned off the carbon monoxide entirely, and they also really reduced the haze. So it's not methane only that's driving this, it's these two carbon species together that seem to be driving even more haze. And if you do a bad thing and compare the x-axes that are completely different between our two sets of experiments, but you squint and start to kind of think, okay, what if our Triton experiment that had way less methane, but a little bit of carbon monoxide, if you plot them in this hacky way that you should not, we made more haze in our Triton experiment than they did, comparatively speaking, in their Pluto experiment. You would have to do the same whole series of experiments within the same chamber because they have all different kinds of practical things that are different between them that could be also driving this difference. But again, this is, I think, really compelling that we should look at this more. If we then go back to what their compositions are actually made of beyond production rate, this is now just looking at the results from the Johns Hopkins experiments. And here's our Triton case and our Titan case. Even though it's a tiny difference in the amount of carbon monoxide that's present, we see much, much more oxygen in the solid haze sample. It's 10% oxygen by composition, even though it was 0.5% CO in the gas mixture. So it's being really readily incorporated and kind of an outsized presence compared to what we put in the initial experiment. And if we then go back to these Van Krevelen diagrams, and now this is again hydrogen to carbon versus oxygen to carbon. This is Titan, and then this is Triton. We're seeing obviously this oxygen get incorporated much more strongly. But then if we turn to a different way of viewing this, where we're looking at the hydrogen to carbon versus the nitrogen to carbon on this side of the panel, we can see that the nitrogen incorporation is also super different between Titan and Triton. And some previous experimental work has thought that maybe oxygen gets incorporated at the expense of nitrogen, but that's not what we're seeing here. We're seeing both oxygen and nitrogen enhanced. And so maybe that's showing us, again, a different pathway when you have carbon monoxide in the mix. We also, again, see here, this, if you remember from those shapes I showed you before, is the carbohydrate region. And so even though we have, comparatively speaking, a tiny, tiny amount of this carbon monoxide in the gas phase, we're detecting a molecular formula that is consistent with the simplest sugar molecule, glyceraldehyde. Again, we can't prove it's there. It's the molecular formula, not the molecule, but pretty interesting nonetheless. We measured the spectra in the visible to the near infrared of the Triton samples that we made. And so in the visible, they're not that interesting. But if you start to look into the near infrared, you start to see features that can tell us again about the functional groups that are present in their chemistry. So here in this region, I keep losing my mouse, you see in this amino group, this NH stretch, and then these various carbon stretches out a little bit further. And maybe here we see the presence of an oxygen-hydrogen bond. It's a little hard to tell. But if we then, again, go and compare this to other work, I'm showing you now spectra from a whole host of different experiments. And I kind of cherry-picked these based on whether they're very widely used, like the CARE experiments that are pretty much everyone's favorite stand-in for a tholin to use in exoplanet models. They're up here, and they also did a Triton case, which is in blue here. But then otherwise, these are mostly ones that have had carbon monoxide in the mixture or that were focused specifically as a Triton experiment, which is what this McDonald one is here. And so you can see they all have this pretty prominent feature in the amino acid or the amino group. But then if we shift here, now we're just looking at the infrared from 2.5 to 5 micron. You can start to pick up differences a little better. So you can see that the placement and the depth and shape of this amino bond seems to change. We also have this bond here that kind of shrinks or grows. And I should say that this turquoise one is my Triton experiment. This orange one here is the phaser Titan experiment. And so they are the most similar, which makes sense. They were made in the same chamber. So all of the other different experimental things that could be driving differences are not happening here. But even here we see this change. So this region here, this feature is deeper and it's wider if you compare it to the Titan, which I think is probably due to that presence of oxygen. There's probably this very broad oxygen bond in the background here of the amino bonding. And then these like carbon nitrogen bonds here seem deeper for Titan than for our Triton mixture. So even though these tiny little trace species amounts are changing, we are actually able to see that in the spectra of these materials. If we go back to, again, this is from the French group, they did an experiment looking at sort of a Titan-like mixture, but then also adding carbon dioxide into the mix. And they measured more towards the UV. And so they saw that as you start to increase this oxygen content, this time from carbon dioxide, you're increasing UV absorption as well. So this doesn't probably just affect the infrared, it might also affect shorter wavelengths. But this also seems to be super dependent on the kind of oxygen carrying molecule that you have, whether it's carbon monoxide or carbon dioxide, for example. So that's sort of your whirlwind tour of all of the things we have learned from the lab. And then the question is now, how do you translate that into something that's usable for atmospheric models to eventually compare to observations? And so I'll kind of touch on just a little bit of what we've tried to do so far. So I've showed you this plot before that we have a handle on the production rate of these hazes as a function of the different compositions. And then we have also a handle on their particle sizes, that they're all relatively small. And so we can maybe treat them, at least initially, as Rayleigh scatterers. And so these are two different examples of works where we've input these parameters. So we're kind of capping the production rate at the amount that we saw in the lab, and then treating these particles as Rayleigh scatterers, and also the composition of particles that we had, showing that they should be oxygen and sulfur rich, perhaps in certain cases, for the L9859 system, which is led by Daria Fedorodetska, who is a grad student now at UC Riverside. And then this very first paper from my PhD looking at the TRAPPIST-1 planets. And so these are the Hubble observations that actually were taken compared to various atmospheric models. And I'm showing that these two orange and purple cases are when we really pump up the haze to make it match the observations that were taken. We're getting an unphysical result. The amount of haze you have to add is totally outside what the labs tells us we should expect for this kind of hydrogen-rich atmosphere. So telling us, at least in this case, haze is not the reason we're not seeing anything for the TRAPPIST-1 planets. Is probably because they don't have hydrogen atmospheres. And then these are predictions from Daria showing what we might be able to measure with JWST looking at this particular set of planets. So we're beginning to tease out ways to apply these lab measurements into models, but it's very much a work in progress. What would be sort of ideal, of course, is if we could measure not just the spectra, like I showed you earlier, but the optical properties, the actual complex refractive index of the absorption and scattering of these particles. And so this is a spaghetti plot kind of showing some optical properties of this whole bunch of different cloud species that we think are important for hot Jupiters. But we have just this one thing that says Tholin, which is representative of the CARE 1984 Titan Tholin experiments, the only one that's widely used, even though we have some others, but not with the kind of wavelength coverage that would be useful for atmospheric models. So that's, of course, what we're trying to build toward is all of these different things I've shown you, which we're beginning to understand the chemistry and physics of. How will that look to a modeler? And it's through this. It's what we really need. And we are working on it actively, but no results yet. And then finally, the thing I'm really excited about with JWST is not only will we be able to start maybe measuring features from these haze particles themselves out in the infrared, but possibly also potential precursors. With JWST, we have access to a whole bunch of different carbon species. So if we can maybe see those as in the gas phase, that can also tell us more about what's happening in the solid phase. So I'm running out of time here, so I want to wrap up. To kind of summarize all the things I've talked about, if you really walk away from this talk learning anything, I want you to know that methane is not the only way to make haze. We can do it apparently with carbon monoxide, sulfur-bearing and other oxygen-bearing species also seem to matter to whether they make more or less haze or changing the chemical properties of the haze, but methane isn't the only way. Hammering that even more, that when we alter these different trace gases in the mixture, that changes the ability of these materials to contain potentially prebiotic materials like amino acids and sugar-like things, and also changes whether or not they'll be good at helping cloud formation happen. And finally, these differences should be observable in atmospheric spectra of these worlds, like with JWST, if we have a very thorough understanding of how the optical properties of these things change with these different chemical and physical differences. So I'll put up the sort of very, very big picture takeaways here. Thank you so much for your attention. I am very happy to take any questions.
Good, thanks, Sarah. I think we are going to one quick question, and not for the rest of the question, Neil actually asked the question first. So there's an email of Sarah, Moran at lpl.arizona.edu. Please feel free to contact with Sarah.
Yes.
And yes, there's questions. Might haze formation in rainout effect on atmosphere's oxidization state? Over what time scale?
I absolutely think it could affect the oxidation state as you're sequestering various gases, out of the gas phase and into these solids that are maybe not interacting with the rest of the atmosphere. Time scale is, because I'm not a photochemical modeler, I'm not going to have a great answer for you on that level, because I can talk to you about, we see these things happen very quickly, over the course of an experiment in the lab where we're running these things for 72 hours, and we do see gas phase changes dramatically over that time scale. But how that translates to an atmosphere itself is not super straightforward. So I don't have a great answer for you there. Sorry.
Right. Thank you very much. For the other questions, please send an email to Sarah, and I will see you next week. And let's thank again, Sarah.